the P30 seminar series. Well, yeah, I see you started the recording, so I was going to tell a joke, but now I'm thinking of maybe I shouldn't, but I will anyway. But for those of you who aren't familiar with Rich's background, he graduated from Brown University in 1977. So that means, Rich, 1955 an important year for you?
Almost off by one, but
okay. Well, you blew my joke. 55 is an important year for me, and the joke, just to tell it anyway, since now I have the 45 people on the call interested, is I tell people that when I tell my group often that in the history of the world, 1955 is a very, very important year because three people of enormous importance had made significant contributions to world history, world culture, were born in 1955. Bill Gates, Steve Jobs, and Bob Mack. Unfortunately, the world has not quite yet recognized my contributions, but I keep telling myself someday that will be true.
It's a good joke.
Rich, he got his PhD from UCLA in 1983 in biomathematics. He then joined the intramural program at the NIH directly as a staff fellow. He stayed in the NIH system until, it was in 2005 when he moved to Yale. Before leaving NIH, he was the chief of the modeling and physics section there at the PET program at NIH. Since 2005, he's been at Yale, and Rich is clearly one of the leading authorities in PET data analysis, and as one would expect, he's received a number of awards honoring his contributions in science. He received the Kuhl Lawson Award from the Brain Imaging Council in 2007, the Edwin Hoffman Memorial Award from the Physics and Instrumentation Council at the Society of Nuclear Medicine in 2009, Distinguished Investigator Award in 2016 from the Academy of Radiology Research, and the Edward Hoffman Award from the IEEE in 2017. And when we were in the process of putting together our two center grants, the P30 and U19, we definitely needed to bring some expertise on board in PET data analysis, particularly for brain imaging studies. And after a considerable amount of pleading and begging, I was able to convince Rich that he was going to join the program, and I'm certainly glad he did, because and all kidding aside, I honestly don't think either of these centers would have been funded if it wasn't for Rich, Carson, and the group at Yale participating. So I'm very grateful for Rich and the generosity that Rich and his group at Yale is showing us by participating in these two centers. So today he's going to give us a introduction and on PET data analysis, and it's the title of his talk is Kinetic Modeling in PET, Madness and Methods, or Method to the Madness. And can't wait to hear what you say, Rich. So I'm going to hand it over to you. Thanks.
Well, thanks, Bob. Thanks for the introduction, and it's been our pleasure to collaborate with you on these two center grants and anything else that's going to move Brain PET forward here. So I look forward to sharing with the talk some of the ideas in terms of doing what we have been doing for a ridiculously long time. So here's the outline of what I'm going to try to get through in the hour, just to kind of do a modeling 101. It's kind of the basics, and here focusing on doing it for brain PET, brain receptor PET, brain target PET, the tracers that have been successful. I'll then walk through that process specifically for our SV2A tracer as an example of the kind of things one does in that process of implementing a new tracer and choosing the modeling that goes with this and what validation. I'll share one very specific example of a positive thing that the modeling can do, which is to separate the delivery effects of blood flow from the binding effects to the target. I'll give some number of examples of places where it matters to model that have been coming with our data, other data in the literature. And then the challenge that we face that, with a few number of sites who want to try to do things the hard way, if we're going to get our useful tracers out there, we've got to get it simple. And we've got to not go to the complicated things, but go to simple things like SUVRs, and how that's a little tricky and why that's tricky. And it can be right, but maybe for the wrong reason. And then I will exercise the pH in my PhD by philosophizing a little about all this at the end. So the obvious kind of thing is we know when we inject a radiopharmaceutical, the image changes with time. This is Henry Wong's serotonin transporter, AFM, with binds to the SSRI, and we show that an early image, 0 to 10 minute post-injections, looks like blood flow, but as time goes on, obviously the distribution changes. And here when we get to the end of the study, end of the scan, out towards 2 hours, the imaging, the distribution looks very, very different now based on the distribution of the target. So as time goes on, the flow information tends to go away, but the target information, here looking for the serotonin transporter, is increasing. How do we go about dealing with that? And that's what modeling is all about. The idea is to say, okay, if I take my time course of data, my sequential images over time, that with appropriate additional information, particularly the input function, how I can use with a model and separate that the images of the radioactivity between blood flow and delivery. And this input function is the time course of the radiopharmaceutical in the blood, the delivery of that. And especially in the brain, that's nice because that's where the brain receives the tracer. So we have a lot of goals. Our really is to build, when we start with a new tracer, we'd like to understand how the tissue measurements relate to the things we care about. We want to account for how that input function changes because that'll be different from person to person and in different situations. We'd like to figure out what we can measure and come up with how to do the study, validate it, prove that it measures what we care about, and even more importantly, verify it's not influenced. So if I'm interested in measuring amyloid load, I don't want it to be affected by blood flow. We'd like to produce cool images because everybody likes cool images, and that gives us the most practical utility of a method, but also like to come up with a simple way, simple practical protocol here to be able to use these tracers. So a few terminologies we'll do. We'll talk about the delivery of our tracer. We'll call that K1, K, because we talk about these rate constants, and that's the first step, coming from the plasma into the tissue. But probably the thing we will talk about a lot more is this volume of distribution. Sometimes you'll call it a DV, distribution volume, or VT. And it would be the ratio if we could come to equilibrium between the total in the tissue and our reference fluid, usually the metabolite-corrected blood plasma. This includes everything, what's free, what's bound non-specifically, and whatever is bound specifically to a target, for example, a protein. And we found it to be very useful for tracers that bind reversibly, not irreversibly, but can come on and off. Now, the world often will look to go the next step about comparing this to this volume of distribution to that in a reference region, ideally a region that's not relevant to a disease. Or even better, if that reference region has no specific binding, we can calculate a binding potential, a bound to free or bound to non-specific ratio. So all of these are the things we're interested in, and they all tie. This is what we can measure, and they tie to how much of the target concentration we might get, as well as its affinity, and separating out from blood flow, which is going to be primarily in K1. There's lots of ways to get these things. This is called job security for the modelers, that they can come up with different methods, often to a fault, and that's where we might get the madness in the methods when people agonize over that. We can just fit the dynamic data. That's how we start. We have something called the Simplified Reference Tissue Model, which can avoid arterial blood. We have verifiable graphical analyses like the Logan plot to avoid complicated numerical analyses, or even we can infuse the tracer, which makes us get things into equilibrium. So let's talk briefly on these. We might do it the hard way, where we collect dynamic data. So this would be a regions of interest in the brain that we're following over time. So each time point is a scan. We get the arterial input curve. We'd be able to reconstruct and get these time activity curves, and then be able to do a fit to be able to determine which model fits and extract those parameters, that volumes distribution, or maybe those binding potentials there. And so that's an example here. We've gone back to that same SSRI binding, the serotonin transporter binding ligand, and be able to separate them into parametric image. So for every pixel, we generated a curve. We extracted two parameters, our blood flow parameter that's in K1, and our binding parameter, volume distribution, and separating these out. And that way we can get the most information out of the data using the entire time course. Now that doesn't mean that a late image isn't kind of reflective of this high binding here in the raphe nucleus, or that the early image isn't reflective of the blood flow. They are, but this mathematically will separate those out. And being able to do that, it requires a lot of work to be able to do that, but it will give us the most accurate separation of delivery and binding. Now, the reference tissue model was a very cool idea, now 25 years old, that recognizes if I have a given reference area, a tissue with little or no binding, or a region that, isn't going to change in disease, recognizing that the same blood is delivering to the reference as the target. With a little bit of math, you can rearrange it and get rid of the blood. That is, skip the arterial input function. You can infer it indirectly from the math. And here's an old image from Roger Gunn looking at two different dopamine markers, raclopride for the dopamine D2 and the sharing compound for dopamine D1. And you get two images, the normalized delivery, this is normalized to the reference region, and the binding potential here showing the high binding in the striatum in particular for the D2 receptors. A nice advantage because it skips the need for arterial blood, which makes it much more patient-friendly, but still requires the full dynamic scan and a complicated modeling. Now, the other cool direction that people went is so-called graphical analyses, because those dynamic curves were just a little scary sometimes. And basically, Gene Logan found a way of rearranging the data to plot it such that the slope of a line would be that volume of distribution. And this is more of a model-independent way. So here's an example here for a serotonin ligand, where we look at the time courses in three regions, but now not plotting the time activity curves, but plotting these transform values as the integral of the tissue value divided by the tissue, or the integral of the blood divided by the tissue. And here the slope is the volume of distribution. We have high binding of the serotonin 1A in the frontal cortex, intermediate in the thalamus, and very low in the cerebellum. And then we only have to decide what time period do we consider this to be linear. And from that we can get that slope, gives us that volume of distribution without the complicated convolution fitting. Or finally, if we can actually come to equilibrium, then we can skip all the modeling. We can put the modelers all out of work completely because we can just measure this directly. We can measure the volume of distribution by just the tissue to plasma ratio. We can get binding potentials by looking at a region of interest to our background or our reference region immediately there. It makes life very, very simple. It also allows for a short scan to be done. And here's examples with an old opiate receptor ligand, cyclofoxy, showing that we can reach equilibrium and being able to do it. This would allow us to be able to just collect an image out here during the equilibrium phase and avoid all the fancy dynamics. So I've just walked you through 4 different general approaches that people use. The best case is we have a molecule where pretty much they all work and they all give similar answers. But in some cases, one's going to work better than the other. So what's our challenge? Well, if we really understand how the tracer works and we've done this validation work, then can we take the next step? Can we make a simple, clinically practical protocol that is patient-friendly and ideally suitable for multi-center trials or multi-site trials for these program projects? And we can do that in a way where we're reasonably accurate. And so, in a sense, anything we might lose by not doing things the hard way will allow us to study many more patients. So that's kind of an overarching goal. Do it the hard way, figure out how to do it the easy way reasonably well. And of course, it's a little hard because very often we might develop the methods in our healthy controls or one population, apply it to a patient population where, for example, we don't want to do arterial lines, we don't want to do 2-hour scans, but we're not always sure that the assumptions will be accurate. All right, so let's move on into this process of picking that model when we first start with a new tracer. And I want to walk you through my favorite tracer lately, of course, which is our SV2A tracer, carbon-11 UCBJ. So how do we do this? What's the steps we do in general? And this is the key process. We identify a target. We're going to do some in vitro work with some chemical matter. Then we have to do the radiochemistry. We'll then do dynamic scans and arterial blood samples to be able to get that, a regional analysis or a voxel-wise analysis. Apply the modeling to figure out how best to extract parameters. Might do some test-retests to see the reliability. Ideally doing blocking studies if we have a patient-friendly blocking drugs. And then doing some validations. And this is usually done with animal, unless we have some resected human tissue, to compare the in vivo maps to what we would measure ex vivo or in vitro. So for this one, we're looking at this particular target, this protein target, SV2A. It's on the presynaptic terminals on the vesicles there. And we'd gotten involved in this because of SV2A's interest in epilepsy and because of the drug Levetiracetam, also known as Keppra. Although this is an anti-epileptic, anticonvulsant, it was later found how it binds to this particular target, SV2A, which is affecting and controlling some of the exocytosis of vesicles, which could be leading to seizures. And there's lots of evidence about the relevance in epilepsy, both in terms of looking at postmortem tissue to show reductions in SV2A. This is in patients with hippocampal sclerosis epilepsy, and a number of other both tumor models as well as knockout mice models, transgenic models there. And more recently, this has become a target used to be able to measure synaptic density, at least indirectly. Remember, we're not counting synapses, we're not doing that by electron microscopy, but we'd be looking at the Western blots of this measure. So this is an example with some Alzheimer's mice, APPPS1 transgenic, which in the hippocampus at baseline have lower levels of SV2A immunoreactivity with their antibodies. And in this case, with a drug trial, with an AstraZeneca drug, was able to recover the SV2A marker, as well as recovering some function. So another marker here that we can use and one we can use in vivo. So what do? We start with in vitro binding, and this is a molecule called UCBJ that we developed in collaboration with UCB Pharma. They're the company that produced Levetiracetam and was marketing future versions of that, like Riveracetam. And with Henry Wang, Nabil Nabulsi, and our team being able to develop this carbon-11 compound, in which we found that it had an affinity of 7 nanomolar and very good selectivity against the other SV2 isoforms, and also that the percent displacements against other forms was very, very small. Now, for some folks thinking about making markers for the brain, an affinity, or at least an inhibitory affinity of 7 nanomolar, might not seem good enough to produce high signal, but this is a case where the amount of this receptor is so high, this target, because it's present in virtually all synapses. Developed the carbon-11 synthesis, radiosynthesis, to be able to do that we published several years ago. Nabil Nabulsi leading that effort with Henry and being able to produce this quite reliably. We've done this hundreds and hundreds of times. Then we start with monkeys. And so here is the initial image, the MR of the monkey, and then this is an average SUV image from the monkey. We show high uptake in gray matter, low uptake in white matter. No big surprise there, and we can measure in the metabolites to be able to look at the parent fraction, and it's reasonable that we're still at 25% parent by the end of the study. We also measure the free fraction, what fraction of our tracer is unbound to proteins, and it's quite high, 46%. And that's very good because that says it's going to enter the brain well. It has a log P right in the sweet spot for getting into the brain. We can do blocking. We have this drug, Levetiracetam, and so we could do this blockade with carbon-11, 2 scans on the same day. We can measure that blockade by looking at the volume of distribution. This was using our MA, one of the graphical methods. And then ultimately move on to validation. That is, we've done a study here in a baboon in vivo, sacrifice the animal, take out the tissue for Western blots, receptor binding assays, and a little bit of confocal microscopy. Here's what the Western blot looks like. So we can see high binding in all of the gray matter regions and very low in the white matter, centrum semivalley, and that is in good agreement with synaptophysin, which has been a previous marker used as an in vitro marker for synapses. We have a very good correlation there. But the more important correlation is that between the in vivo measure coming from the PET imaging, from the VT, against these various in vitro measures, whether it be the Bmax from the receptor binding or the optical densities looking back and forth. So into the point of trying to say, yeah, this looks like we think we know what we're measuring. We're measuring this protein accurately in the brain. We go to humans, and we measure the input curve. This is from arterial samples. We can measure the metabolite profile, starting with the parent compound only, and then the development of radiolabeled metabolites over time. That lets us measure these fractions. And again, something not too dissimilar from the non-human primate, about 25% parent towards the end of the scan. Here's the example of the images. We have very high uptake of the tracer, up to SUVs of about 10, which means we're going to get very good count level, very low statistical noise, and as well as seeing that clearance of the tracer, which says that the binding is reversible and that we're going to be able to use those models, those volumes of distribution we described before. Then we do the modeling. So what do? Okay, we try a very simple model. We have K1, which would deliver the tracer, and K2, 2 parameters. Lets me measure the delivery K1, and from the ratio, I can get that volume of distribution. And we try a more complicated model. Well, here, we're lucky that basically you cannot see the difference practically between the 1-tissue model and this more complicated 2-tissue model. That's going to help us a lot in terms of giving us a highly reliable measurement. We plot the values, and we get very good agreement in virtually all regions, virtually all animals. So this gives the values of those volumes of distribution. We're getting about 20 in the gray matter regions, occipital cortex, parietal, etc. So in other words, at equilibrium, there would be a ratio of about 20 to 1 brain to blood. White matter, much lower. That's good. We don't expect much specific binding in the white matter. And even at this stage, that number even gets a little lower when we refine the region of interest. K1's our delivery. That's related to blood flow, but partially it's also limited by how well our tracer extracts. That is, when it reaches the capillary, what fraction of it gets across. With K1s in 0.3 and 0.4, it suggests about 50 to 60% of the tracer is probably getting extracted, which means we will be sensitive to blood flow. That's a nice thing. So now we can measure two things, a blood flow measure, not perfect, but related to blood flow, and this total binding, both SV2A as well as nonspecific uptake. And now we go through our processing scheme. For each subject, we have the dynamic PET. We have an MRI, so an MP-RAGE MRI, and we'll have a template. And there's numbers of templates that could be used, being able to do that. The template will register to the MR, which will be registered to the PET. The PETs are all registered together for motion correction. And then we can immediately get these time activity curves. So this is a very nice automated process to be able to generate curves from which we can apply the different models. So we can apply those different models. This is like the reference region model, what may be. And if we can apply that to a region, or we can apply that to every voxel, like the example we showed before. And here we get a binding potential image, this one for the serotonin transporter. And with the template, we can immediately extract the binding potential values, or the VT values, and get them very, very automatically. With the database and the processing scheme for a molecule we've characterized, by the time we've done a scan in the middle of the day, these numbers are in the database by the middle of the night. We did test-retest. This is with carbon-11, 20-minute half-life, so we can do 2 on 1 day. These are the percent differences we got in each region for each of these subjects. These are exceedingly fabulous. These are exceedingly reliable numbers. We've never had a tracer quite this good. And we're doing so well because we have a very high uptake, so we have good counts. We have a really simple model, that one tissue model, to get the volume of distribution. And the metabolites are reasonable, so we can measure the input function well. That gives us this great reliability across the board. And that lets us, because of that high value, do those calculations pixel by pixel. So here what you're seeing are images of the volume of distribution, where we took each pixel, produced its curve, fit it to the one tissue model, and here created an image where the value is not radioactivity anymore, it's the volume of distribution. Here, therefore, numbers from, for example, in this case, up to 30 or 40 ratios that we're getting in different voxels. And here's the test and the retest. And the nice thing about this one is that the images, the quality is so high. Often for some tracers with poor uptake, we need to blur the images to avoid noise. Here, not the case. So we can get quantitative markers. And also means we can look at them at very small structures. That's going to be very, very relevant if we want to be thinking about that in the focus of an epileptic seizure or looking at a small structure in the midbrain in different diseases. We also do this step. We want to say, well, how long does this scan have to be? We collect the scan for 2 hours, which may seem a lot for a 20-minute half-life. We have a high-resolution scanner, high-sensitivity scanner, the HRT, and that means we still get useful data. But we can simply just take the data and chop off time, go back, say, okay, instead of 2 hours, let me analyze 90 minutes, 60 minutes, 30 minutes, calculate the volume and distribution, and say, how does that compare to the value using the full data set? And so we certainly find if we can get down to 60 minutes, and our percent differences are very, very small with small additional variability. So 60 minutes is more than enough to get the full dynamic data, and that's what we're doing there when we're doing these dynamic scans. And fortunately, we have a drug we can use to displace the tracer, and that is really producing high confidence that we're measuring that target. Here we did it a little differently. We infused the tracer to reach an equilibrium, so we could do that here. In this case, we were able to get to equilibrium. And then we did a second scan with the same infusion, and then we gave Keppra right in the middle, and we could watch the displacement of the tracer go. So that really is nice, and it's a nice luxury with this target, which is often not the case with other targets, for example, amyloids or tau, where blocking of that is not an easy thing to do with a drug. Here, a drug that's been given millions of times to human beings. Okay, there's still a lot we have to do with this one, which I won't belabor here, but I will come back to some of the issues here that we want to think about in terms of developing, taking the understanding of a molecule and turning it into a useful version. So one issue is the outcome measure. What's our basic primary outcome measure? Is it the volume of distribution? We need the arterial data. It also includes nonspecific binding. Should we correct for the plasma free fraction? We said we could measure that that would be relevant if there are group differences or a lot of variability, and we found that in some populations. Should we calculate a binding potential? Well, that'll need an ideal reference region. Or do we just want to take a ratio to a suitable region? It won't be just the specific binding that we're talking about here, but it still might be useful. We found this to be useful in Alzheimer's, where we found that our cerebellum gives us much less variability in our measure. And if we accept that cerebellum is not different in the disease, and we validated that by looking at the VT in the cerebellum, it tightens up data. But the other alternative is, what's a good reference region? Generically, we've been using the white matter because there's little or no SV2A there. The Western blot said little, but, with our blocking studies, we have found there's a little bit of specific binding. We've checked, as we said, there's no difference in this in some disorders, but we did see, for example, differences in MDD. Also, this is a very small region, the Centrum Semi Valley, so it's going to make things noisy, and we have to be very careful about partial volume effects there. So the summary there is, there are many good answers for this, but it doesn't have to be the same. And something that's disease-specific would be very reasonable. But when we start, we'd like to use the absolute measure, and we'd also like to look at that, at least in a subset of patients, to say, is our target normalizing region something that we can use because there's no differences there. And, of course, this was carbon, and thanks to great work with Henry and Jason Kine, Nabil, we have fluorine-18 versions, very similar molecules. We've just removed one fluorine because this was very difficult to label with 3 fluorines in that phenyl ring. And we've recently published these data, and we find basically that it's behaving identically. And this is going to really help the translation of this molecule out to the world. So we're excited about that. All right, so let me give one very specific, a positive example here about using modeling to separate out. We saw that, I showed you those images where the radioactivity images have a mixture of blood flow, delivery, and binding. Now we could separate those out. And this was driven by the SV2A that we were wondering about, the purpose of this protein that's sitting on these vesicles, when you activate those presynaptic terminals, we're going to release those vesicles. They'll be exocytosed, they'll be recirculated, clathrin-coated, and then recycled. Was that going to change our signal? In other words, will our signal be sensitive to local activity in some way? Or is this a kind of like an in vivo Western blot of the amount of this protein that's in the tissue? So we did a study with activation. Went back to the past when we did a lot of activation studies. And we did 2 scans, a baseline scan and a scan where they were doing visual activation here with these very stylish goggles, shown here by one of our research assistants. And we used 8 Hertz flashing checkerboard, one of the most dramatic stimulus for the primary visual cortex. And we also did fMRI in the same way, just to compare that. Back in the day, we used PET to validate fMRI. Here we're kind of doing this in reverse. And of course, we counterbalance the order in those studies. So here's those results. So first, let me look at the K1. Remember, K1, that's our delivery. We would expect a big increase in K1 in the primary visual cortex. And we got that in all subjects. Big significant increase in K1. We could see that visually in the mean image there, of the mean K1 image, again from the parametric. Big increases in the primary visual cortex, as you might expect. No changes in a control region, temporal cortex, or in the white matter. How about the volume of distribution? Did regional activation here in the visual cortex change our signal? No, it did not. We saw the volume of distribution did not change. No mean change in primary visual or in the other test regions there, which allows us to create that binding potential, again, seeing that we get no change here. So that suggests, based on this one activation paradigm, simple visual activation, that it's a stable measure in vivo of the density, and that we can separate out the flow. And the modeling was key to that, because, again, at any given time, the image has a mixture of blood flow, as measured by K1, and the binding, as measured by VT. And an interesting one, if you looked at the change in K1 that we got, compared to the change in the bold signal, here's the mean value across our 7 subjects, and we got a very nice correlation. So that means also at the same time, the modeling gives you a measure of function related to blood flow, as well as a function of the target. And this has not just been true with SV2A, that's been seen in the amyloid scans, it's been seen in tau scans. And it's important to measure that's going to be relevant in disease models. We're getting a measure of binding of our target, and measure of flow is relevant. In our first study with Alzheimer's, we saw that the patterns were different. The flow changes, we saw changes in temporal parietal regions, in precuneus regions, which we did not see as well with SV2A. Turns out with a bigger sample, we could see it, but it wasn't there. So again, by doing the modeling, we can get at least these two measures, a blood flow, a functional measure, and our binding measure to our target, whatever it might be. And that's going to allow us to get 2 for the price of 1 and be able to ask multiple questions that way. All right, so let me give some example, giving you a feel for that in that kind of the positive states. Let's look at some cases where examples were when we needed the modeling to help interpret what we're doing. So sometimes, and I'll point you to this very nice paper from Adrian Lemertsma, who was just looking at the case for doing quantitation. Here's one example he quoted in his paper. This was in the Journal of Nuclear Medicine a couple of years ago, looking at test-retest here for amyloid, I think in older controls. And when you did the modeling and calculated a binding potential, the data were much tighter than when you just use a ratio, a normalized ratio of one tissue and another. So when the modeling is done right, you can get less variability. But you have to do things right for that to work. And it certainly works in many, but not all cases. But the one I want to focus on here is, of all those goals we had, is the issue of the input function. If you remember, when we inject our tracers, the particular state of the person, everything from their demographics, their particular physiological state will affect the time course of the tracer in the blood, that input function. But also, other things can affect it. So imagine I'm trying to study some drug effect. I have a target drug, I'd like to see its interaction, and that we have a tracer that binds to the same site. Okay? Here's what we'd love to see. We'd like to make a baseline scan, and then as we gave a dose-dependent increase in our competing drug, we would get a dose-dependent response in our measure. Okay? And life would be good. That'd be nice if we would just get that. But here's the trick. When we give a blocking dose of a drug hitting a target, it will reduce the target, but it may increase the tracer availability. In other words, if I'm blocking this site all over the body, the bioavailability of the tracer goes up. That's going to increase our input function and will increase our non-specific uptake just because there's more around in the blood. And so what happens? What wins? Do we get this nice dose-dependent response? Because we have one thing going down, the specific binding, but we have one thing going up. It might be a big effect. It might be a small effect. And it really depends on the distribution of the target as well as the tracer kinetics. So let's look at some examples in some real data. Here's one of the most extreme cases. This is back to that serotonin transporter tracer AFM, where if we give a blocking drug, citalopram, we get a huge effect on the input curve. Here's the input curve. The white is the baseline curve. The blocking curve is in yellow. This is a log scale. There's a huge difference that when I block, I have a huge amount of more availability of my tracer, but it actually clears faster. And this is because there's a lot of specific binding of the serotonin transporter in the lung, and for an IV injection, the lung gets the first cut. Now, the blocking works, but quantifying it without taking that into account would be very problematic. Here's some examples where that's even clearer. So a few years ago, we were doing some monkey studies with giving LPS, giving other things to both activate and deplete microglia. So we gave a CSF1R blocker, PLX3397, that blocked the binding, of this case PBR28, and then 12 days it returned. So we saw a big drop when we blocked the microglia, or if we gave LPS, we saw a big increase. Here we're doing it with the modeling. These are volumes of distribution images up to a scale of 75. If we just looked at the SUVs, however, not quite so clear. PLX, we saw a reduction, but it wasn't as dramatic. LPS, we saw an increase, but it wasn't very dramatic. Now, why is that? Well, that's because the input function changes too. When we deplete microglia throughout the whole body, the blood availability goes up. And therefore, the uptake in the brain now is more non-specific than specific. And the reverse happens with LPS. So again, an activation or a deactivation is going to affect both the target and the bioavailability. Or here's an interesting one with a different target. This is for looking at an enzyme for 11-beta-HSD1, the enzyme that maps cortisone into cortisol. Here's the distribution within the monkey brain. It has a very unique distribution with high uptake in the occipital region, progressively less in the frontal. We gave an inhibitor. It looks like it blocked very, very nicely, but let's look a little more carefully at the numbers. Here's the time activity curves. In the occipital cortex, high uptake. Here's the baseline in blue. Here's the blocking. Oh, that's nice. Nice blockade. Now we'll go to temporal cortex. Well, now looks like the blockade is smaller. If I go to the frontal cortex, well, now the blockade went up. Yep, instead of going down. So what's going on? Well, this one's just, it's those two effects the blocking of the specific uptake and the increase in the nonspecific, but the relative effects matter. So we can look at it this way. In the occipital cortex, there's a lot of specific binding. We've blocked a lot of it. The nonspecific also went up, but the net effect went down. In the temporal cortex, less specific binding, same amount of nonspecific. The specific goes down, the nonspecific goes up, the net goes down a little bit. In the frontal cortex, with even smaller specific binding, the net effect is going up because the nonspecific goes up. Without the modeling, if all we had was the uptake levels, we would not be able to take this apart without understanding those differences in the input functions. Okay, so we've talked about the main ideas of modeling, the specifics in the SV2A tracer, example of using the separation of blood flow and the specific binding, and some examples, especially with input function changes, how modeling is important to account for them. But let's see if we can use our understanding of these things to make life simpler. How can we simplify this? How can we make these more patient-friendly? Okay, well, what we'd like to do is say, okay, I understand the model now. I've done my homework. And now I'd like to produce a protocol and analysis scheme that makes it simple. Perhaps a short scan, maybe a reference region. We can skip those nasty arterial samples. Maybe just a simple short scan. That would be best. And that could be very important for some patients where 90-minute, 2-hour scans are just not practical. And especially if I can find a period that compares well to the distribution volume ratio. In other words, I can do both the simple protocol and the complicated protocol and correlate those two. And hopefully we can do that with just the standard uptake value ratio, just a ratio between the radioactivity in the target region and the reference region, and hopefully that matches our model base, and life would be good. Well, this is very, very common in our field because it's going to let us apply this, and it's going to let it make it easy to go to sites where arterial input functions are just not a reality. Lots of examples of that in the literature. Here's a couple recent ones in the tau imaging. 2 different sites came out in the same month of Journal of Nuclear Medicine. And what do? They generated these plots, and we're really good at these plots. This is the gold standard on the x-axis. X-axis should always have the gold standard. This is the SUV ratio. This is the simple imaging measure. Just say scan from 60 to 90 minutes, take a ratio. Here we're taking ratio to cerebellum. How does that compare across different regions and different subjects to the gold standard from here? This is a 2-tissue model. 2 different people, and what they did find is they could find, yes, we could find a time period, which was good. You also notice that that time period was, here's for different subjects, looking at a time period, and at least it's going to be very linear. Here, looking across many, many subjects. And you notice a little bit they compare different time periods. And that's the nice thing when you have a complete data set. You could say, let me try different time periods, see which one gives me the best relationship that I like. Okay? So we did this with our SV2A molecule. We did 90-minute scans and the HRT, and then we compared a lot of different time periods. We did 2 comparisons. First, we wanted to say, okay, can we get the volume of distribution? Well, that's, again, is supposed to be the tissue to plasma ratio at equilibrium. Well, we can just compare that to the tissue to plasma ratio at different times. Or we can do a tissue to reference region ratio, a standard uptake, SUVRs as they're called, and compare that to the distribution volume ratio and see how that worked. Well, first we tried comparing tissue to the plasma ratio, and that didn't work too well. We got much higher apparent ratios than the values we got from the modeling. And this has been well understood for a long time, that when we're not at equilibrium, and a bolus injection, we're not at equilibrium, that ratio is going to be artifactually high, which means we need to do some kind of modeling to interpret those data. Now, it turns out if we look at a ratio, tissue to reference region, in this case, this reference region is the white matter, and we compare that to the binding potential here doing the full modeling, so the full modeling on the x-axis, simple ratio on the y-axis, and we found a time that produced really excellent results with great relationships. This is across many subjects, across many regions. Pretty good. Well, why did that work? Well, we went further, we went further to say, we looked at this in cases, we looked at this for our comparison of Alzheimer's and healthy controls. This was the difference we saw in the hippocampus in our first cohort, and we were able to replicate that using the simple tissue-to-tissue ratio, or SUVR ratio. Cost ourselves a little significance, maybe there's a little more variability, but not too bad. That was encouraging. And the trick there becomes that this is a time-dependent factor. For example, if I went early, 30 to 60 minutes, Well, now my ratio is underestimating the model-based value. 60 to 90, well, that's the Goldilocks time that gives me the best agreement. If I go even later, 90 to 120, well, that's overshooting. This is completely expected by the modeling. As time goes on, the ratios are going to get higher and higher, and we can find, for a given tracer, for a given application, the sweet spot of where that's going on. So let's think about that a little bit. How is that happening? We're going to do a little something with, because what we found over the years is that if we give a bolus injection, as time goes on, the tracer, if I measure the ratio of the tissue to plasma, the tissue, all the regions eventually reach a constant. Now that could be very long. It could take a long time to get there, but ultimately for most good tracers, we can get that within a couple of hours. If I have a region with a lot of binding, that takes a long time to get up there. This is with that opiate receptor in the occipital cortex. I get to that ratio fast. The thalamus with lots of binding takes a lot of time. But one thing we've learned, the math of this can be able to show that if I just look at that ratio, tissue to plasma, this is going to exceed, this apparent ratio, tissue to plasma, will exceed the true equilibrium value, the VT. And this turns out to just be due to the plasma clearance. The faster the plasma clearance, the greater the difference. And also, the regions with the highest binding have a bigger bias. So that means not only will the tissue to plasma be wrong, as we saw with UCBJ, but even the ratio, because the error will be higher with the high binding regions than with the low binding, just because the tissue is slower to clear. Let's play with that a little bit. So here we're going to do a simulation. This is where we modelers love to live, where we create the data. Okay? So what have we done here? We said, okay, I'm going to create a reference region. It's going to have a true volume distribution of 10 to 1 should be the ratio. And my target region is going to be 20 to 1. I have some specific binding and some non-specific binding. Okay, and so what did we do? We're going to simply imagine infusing the tracer there to come, and we'll have it come to equilibrium. This is a case where there's no plasma plate. The blood is just flat. What happens? The reference region reaches its value. The target region reaches its value. It takes a little longer. It always does. If I calculate the ratio between these two regions, the distribution volume ratio, once I get out late enough, I will get to the true value of 2. And we could do that analysis, and if we had this kind of input, we would say, okay, we reach equilibrium by about 70 minutes, scan here. Good. That's perfect, because this is the target, that 2, that's what we'd like to measure. But now let's be a little more realistic, and let's say, well, suppose there's a little bit of plasma clearance. In other words, the blood's clearing a little bit. Okay? So this is the tissue, and I'm plotting tissue to plasma ratio, the reference region, and now it's exceeding this, but just a little. And the target region is also exceeding its level because it's not at equilibrium by a little more. If I look at the ratio, I say, well, I'm exceeding it if I go long enough. So maybe instead of scanning here, maybe I will just scan a little earlier when I get my sweet spot. All right, well, let's do this in a more realistic phase where we might have more rapid clearance. Because of the clearance, in a sense, the brain is having trouble keeping up with the blood, and therefore it falls behind, its ratio is higher, and in the region with a lot of binding, it falls way behind. Now the distribution volume ratio is going to way exceed the true value. Again, this is the value I would get if I took out the tissue, incubated, and calculated the receptor target compared to what's going on with the tracer in the blood. So here I could scan even earlier, but it's funny what we're doing here. We're kind of cheating, okay? And here's an example from a paper Ansel Hilmer put together of looking at, depending on the rate of plasma clearance, it's called beta, depending on how fast that would be, what the biases would be, what the ratio would be. So we'd like this to be true, that would be white, but we can be overestimating or underestimating. It's a function of the value and how fast the clearance would be. Okay, so this summarizes. When we just give a bolus injection, when the tracer is clearing, this tissue to plasma ratio is not going to be the correct value. It's going to exceed the equilibrium value. And the faster the clearance, the bigger the difference. And regions with higher binding, that's often where we're interested, have even greater bias. So therefore, if I just take a ratio, an SUVR, ratio of tissue to nonspecific, I can calculate that ratio, but I will be biased. I will be high. It might be a little, it might be a lot. But it's also true that, well, if I don't wait for the end, I can kind of cut my losses so we can help. That is, we can get a more unbiased answer if we scan early. And of course, scanning early is usually a good thing for the patient. So what we have is two wrongs making a right. We could wait all the way to get to equilibrium, but at that point, because the blood is clearing, we will overestimate the DVR. If we scan early, we can cancel that error out by getting the right value. So I have one factor causing me to overestimate the true ratios, and one factor correcting that in some way. So what could possibly go wrong with doing this? Okay? And the trick is, will we always get the timing right so that the two effects cancel out? Now, of course, we do this very careful study in our initial patient populations, and we verify that time. And the trick is that going to carry over to every population that we do? You know, this was an example with that amyloid data. When we just used a single time, the data were more variable, and that's probably reflecting some differences in clearance. Will we evaluate this in every population? Will we do it as a function of age, as a function of sex, in every patient population will we have? And if we're giving drugs and looking at effects, does the drug affect the plasma clearance of the tracer? In other words, that will affect the beta, that clearance rate, as we found that it did for the serotonin transporter. So here's some kind of summary thoughts for everything we've been talking about now, to think about that. Why do we do kinetic modeling? It really lets us understand with great accuracy what we can measure and really try to extract the most out of these precious tracers and these precious human studies. But doing it perfectly right may not always be the most important thing we need to do, okay? Because as a general rule, our studies are very complicated. We need blood time activity curves, arterial lines, radiolabeled metabolites, dynamic scans, and they cost more, both in time and effort and probably money. And so what typically means is we're going to have to do the modeling studies, we can't usually do as many patients, both at a given site, even the sites where we have these capabilities, and especially in sites where that's not part of what's available. So the trick is to use modeling to produce that patient-friendly assay, something that will give us the best balance between accuracy and simplicity, okay? Because honestly, I expect that we'll be able to get it be more useful to get a lot of patients there. However, we have to keep in mind that these simpler methods, as you saw, come with lots of assumptions. And those assumptions are routinely ignored. Doesn't mean things are wrong when a simple method is done, but it's just something to be keeping in mind when we look at data and we think about something that's practical, especially for patients who are more fragile, who cannot withstand the kind of complicated studies that we want to do. So here's what I would consider my take-home messages. With a brand new tracer, we need to do that first, the hard part, and get a reliable model and a well-validated tracer. And that's really going to be very, very powerful for what we're trying to do if we can be able to understand that. It's kind of a necessary thing. We'd like to understand everything that's affecting it, how the flow is affecting it, how nonspecific binding, how peripheral metabolism is going. I haven't even mentioned the fact that sometimes our tracers produce radiolabeled metabolites. Well, they go back into the brain. This is where our blood-brain barrier tends to help us, but it's not perfect. And can we, get those validation studies? Because very often people dive in. Sometimes it's hard to validate. We were lucky with SV2A because we could give a specific blocking drug to humans. That's a nice thing to be able to do. But the real thing is the next step. Use this understanding to really find the appropriate simple protocol for a given clinical question, biological question, given patient population. Right now, most of the time we're just kind of picking this sweet spot time and saying, oh, this time period agrees, and now we can do a simple scan. But we'd really like to think through all those factors that would corrupt that with the blood work. Can we improve this? Can we validate at least that in a new patient population or under a new drug, that the time course in the blood is not changing? And really think through how those things might affect given specific study paradigm. And we can come up with corrections. Some of those are possible. I didn't show those today. But the other part is not to give up on dynamic scans. So in a lot of our studies, depending on the patients, if the patient can handle a dynamic scan, we'll do it. If that's beyond the scope of what they can do, the arterial line won't work. We might collect simply the short scan, and that will give us both. We'll have a subset of the data with the full dynamic scans, and we'll have those patients, but we won't lose the data in the other patients where that's not practical. We can analyze the data both ways. And because when you do the dynamic, you're correcting for these effects, and that's very nice. And you also can separate out, get two for the price of one again, a blood flow measure, a functional measure, as well as our target binding measure, as we've done with SV2A here. So this would be the image I would normally show in pre-COVID time. This is what it looks like today. So we're a little bit more isolated in terms of the group, but it's a great joy to work with the great team at Yale for all of the different preclinical, clinical, tracer development, chemistry, et cetera, that we do today. And we wouldn't be, these data or none of these steps would be done without them. And I'd like to thank them and thank you for your attention.
We should unmute and applaud you, Rich. That's wonderful. It's always dangerous to have a question from somebody who's not technical as the first question, but could you say something about bolus plus constant infusion and how it can help?
So that's an example in one of the ways of being able to simplify the process, that for certain tracers where that works, where we can reach an equilibrium, you can start that infusion with the patient outside the scanner, reach an equilibrium, which you have to validate in enough subjects, and then just put them in the scanner for a short scan. At that point, you would get the activity in the tissue, and you'd be able to compare that to other regions or to the blood. At that point, if you can demonstrate it that the arterial and the venous blood are at equilibrium, you can use venous samples or just use the ratio to the reference region. So,
someone who's typing, could you please mute yourself? Yeah. Thank you. That's helpful.
So the trick is that, Anna Rose, is that not every tracer can become the equilibrium reliably within the scan time. So for carbon 11, that's a big push. Fluorine, that's a lot easier to do, although that's still not perfect. But it's a nice path. It skips the need for the time course. You just use the image directly, the volume distribution. You lose the flow information because all that happened early. But it's one of those where it is a nice protocol. We found that useful, for example, the mGluR5 molecule, where we validated that approach. What's also nice is I can take one synthesis and use it for multiple patients because they only need to be in the scanner for 30 minutes. So we separate our injections, say, by about an hour. We do one, we let the uptake period, put them in, get either a CT or a transmission scan, a short scan, can bring the second. We've done up to 3 subjects in a row with one synthesis.
Whew. That's pretty impressive.
Which is nice in the days of,
yeah,
what's your grant when you go a little further.
Makes my head spin to think about 3 patients in one day. I can't put my head around.
The best case is 3 different, multiple patient protocols, so different groups are recruiting if they're using the same tracer. So that helps a lot.
Right.
Hey, Rich, this is Bob.
Yeah.
That was a fantastic talk. You have certainly given us a lot to think about as we start down the road for both the P30 and the U19. So the one thing that jumped out at me was the free fraction for the SV2A ligand, 46%. I can't recall a small molecule and usually you see peptides that have free fractions that high. I can't recall a small molecule with a free fraction that high. I mean, number one, that is unusual. But my question is, what is the lower limit for free fraction do you look for? Because we struggle with this all the time because we have some very sticky compounds.
That's correct, right? And it's a great question. So it's when you think of it. So say we certainly find even with molecules with free fractions at 10% or 5%, they still get in the brain pretty well. Because in most cases, even if 90% is bound to the proteins as it reaches the capillary, there's more than enough time in that 1 second of capillary transit to get off of the protein and get in. And so you'll still see reasonable K1 values even with free fractions being very low. The real trick becomes the ability to measure it well. I mean, we do that with ultrafiltration. To do that really reliably, once we're getting down below 10%, 5%, we're not going to measure it well. And that becomes a worry for tracers where we're trying to do absolute values. We're absolute in the volume of distribution. If we don't have a reference region, because we have a reference region, it cancels out, we don't care. If we don't have one and we don't know, if we can't measure it reliably, is the free fraction different in one population than another?
Yeah.
And is that driving? if we just see these global changes, and these are not uncommon in a lot of targets, is that a real thing or is this a free fraction difference? So all things being equal, we'd love to measure something 10% or higher. We can usually do that pretty reliably, something like that. We've certainly gone lower than that and still gotten useful tracers, but it's hard. There's some lot of ones. I mean, that I showed you that 11-beta HSD1 ligand, and it's under 1% free. We do not know that, but at least it has an interesting distribution with the brain, so we can use some kind of reference regions in those cases.
Yeah, because some of the amyloid agents have pretty low free fractions, right?
That's correct.
Yeah,
Yep,
and they seem
absolutely.
to work okay. Not great, but at least they
get
work.
okay. And even with them, the K1s still give them some flow information because it isn't stopping it. I mean, it's an interesting story because the other thing that sometimes comes is if the molecules are charged a little bit at physiological pH. That's because we've got some that are 70 and 80% free and still getting into the brain, but often there's that spot where that's where the log P is going down. Perhaps some of it's charged and it's not getting in the brain as well. So that's the UCBJ and the Synvest one just nailed the sweet spot here with virtually everything. So we'll take that as our lucky tracer for maybe for a career. We'll see.
So you really saying
I just want to say,
5%
Rich,
your lower end for free fraction?
Say it again, Bob.
What were you really saying your lower end is then? Because I thought I heard 1% as being more the.
So 1%. I mean, we're not trusting we do not have a reliable measurement at 1%. Around 5, we're beginning to get some kind of reliable measurements there. Certainly, I'd love it to be 10 or higher.
Okay.
Rich, I just want to tell you, you win the award for the largest audience so far in any of our seminars.
Well, Hank, I paid people to come, so I think that's probably why.
That's right. It worked. That was great. Thank you.
Well, Rich, what I should also say is I just got an email from Bill Gates, and he said that he was so impressed with your talk today, we're going to make you an honorary member of the people born in 1955. Okay?
1955. Thank you. Yeah, well, I'll tell my mother she was late. So.
All right. Well, that was really fantastic. I'm sure if there are no other questions, I think we're getting close. But again, I think people now have an excellent sense as to the importance of what you bring to our two centers. It really is an area of expertise that is very well needed at Penn, and you are, as we could tell from your talk today, one of the truly leading people in the world in doing this type of data analysis. It's just a pleasure to have you on, not only for your scientific expertise, but your good sense of humor to put up with my very bad jokes.
I can match you joke for joke, bad joke for bad joke. There, just ask my grandkids. Okay.
Thank you very, very much, Rich.